Hello everyone, welcome to the session on analysis and design of algorithm. So in today's session we are going to learn what all the asymptotic notations we have and what are the different types of notations we have, and so how we are going to represent in those asymptotic notations. And in the previous class we have learned that so how the order of growth may vary from one algorithm to another algorithm. As we know that for a single problem we can have a multiple solution. Here for among those multiple solution, which one will be the best one? So based on what the number of iterations we are going to count that. So in order to represent the time efficiency of any algorithm, so we are going to make use of the order of growth. So that means that so for a given input the algorithm behavior may change depending upon the inputs varies. Okay, so how large you are going to give the input, so definitely the time complexity will also grow exponentially, or so linearly or quadratically or cubically, right? So in order to compare the algorithm efficiency of two different algorithms for the same problem, so we are going to make use of this asymptotic notations. So why we are using asymptotic notations? In order to compare the behavior of the algorithm between the two different algorithms or more than two algorithms for the same problem, we are making using of based on what the order of growth of the algorithm. So we are making using of this asymptotic notations. So therefore, so in today's class we are going to learn what are all those asymptotic notations in order to compare more than two algorithms order of growth of the algorithm based on the basic operation whatever we are going to perform. Okay, so now let us see what are the different types of asymptotic notations we have. So here basically we have three different types of asymptotic notations we have. So first one is big O, so which can be represented using this notation, okay, big O. Okay, next we have the next notation we have is big omega. Okay, the next one is big theta, which is going to be represented using the notation is big theta like this. Okay, so using three different notations we can represent our algorithm's order of growth of the algorithm efficiency in terms of what the number of times the basic operation executed. Okay, so here, so say for example if you have any problem like if you consider the sorting problem. Okay, so for the single problem we have a multiple solution, right? So you have a selection sort, you have a bubble sort, you have a merge sort, quick sort, so many solutions are there. So now for each solution we may get different time efficiency. So that is the time efficiency function whatever we are going to obtain, that will be different. So that is for selection sort it may take n square of times. Okay, so as your n increases, so the efficiency, that is time complexity, grows quadratically. Okay, so if you consider the merge sort, then the algorithm efficiency is n into n log n. So that means that, so here, so if you compare those two, so n log n is the minimum one. So here in order to compare those algorithms efficiency in terms of order of growth, we are making using of this order of growth, sorry, asymptotic notations. Okay, so usually whenever we are representing these asymptotic notations, as we learned in the previous class, for some kind of problems we may obtain the best case worst case and average cases. So whenever we are doing the analysis, we need to look into what the parameter, that is input parameter, we need to look. Okay, along with that input parameter, if you encounter with any other extra factor, then we will go with what? So we are going to calculate the time complexity of the algorithm based on worst case, best case and average case, right? So usually whenever we are representing the best case, worst case and average case, we are making using of the big O for the worst case analysis and big omega is for the best case analysis and the big theta is for the average case efficiency we are going to represent. Okay, so that is the terminology, or else we can represent your order of growth in terms of big O, big omega and big theta also. So usually we are making using of this one, big O for worst case, big omega for best case and big theta for average case. So we are using. Okay, so if not, the worst case can also be represented using among these representation. So let us see one by one how you are going to represent the order of growth of the algorithm using these asymptotic notations, and what are the criteria or the constraints for representing our order of growth in the asymptotic notations. So what are the constraints for big O, what are all the constraints for big omega, what are all the constraints for average case, that is a big theta, we are going to learn one by one. Okay, so let me talk informally. So usually the order of growth, whatever we are considering, that will be represented based on what? The highest order degree of that particular equation, right? So here also based on the highest order degree only we are going to measure the order of growth. So here in order to represent that worst case, so that is we are going to make use of big O and then big omega and big theta. So if you are talking in terms of worst case, so this represent the upper bound of the algorithm and then this represent the lower bound of the algorithm. As the name itself it is indicating, so informally I am telling. So if the algorithm efficiency grows worstly, so that is, so by that time the upper bound is going to be represented using big O notation and then the big omega is going to be represented for lower bound one. Okay, and then big theta is going to be represented for in, so it is going to be lie between upper bound and lower bound. So here let me take one by one, that is big O notation. How we are going to represent the algorithm efficiency in terms of big O notation. So if you consider this, definitely it is a mathematics, so everything starts with an assumption. So let us consider, so in order to define this, let T of n be the function, so that is be the time efficiency function of an algorithm. So here in order to represent the time efficiency of any algorithm, we are making using of a function called as an T of n. So if you are saying if your function T of n is to be represented in this big O means, so then what is the criteria is the function T of n is said to be or belongs to big O of n. Big O of n is said to be big O of n, which can be represented like, so your T of n belongs to big O of given g of n, the big O of g of n, sorry, this is g of n, if and only if. So this can be represented, the notation whatever I have written in the English statement can be written as T of n, that is the function, the time efficiency function, belongs to big O of g of n. So that is nothing but this is your the degree of a polynomial equation whatever you have obtained to calculate your T of n. Okay, so that is the converted equation we can say. So that is the g of n. So if and only if, so is this said to be in T of n if and only if it should have a constraint. So it follows some constraint, that is your T of n should be lesser than or equal to for every constant c into g of n for all n greater than or equal to n naught. Okay, so once I come up with the example, I will explain what is this n naught is. Okay, so for this, so here our time efficiency functions is said to be belongs to represent, it's going to be represented in big O, can be denoted by T of n belongs to big O of g of n if it follows the criteria or the constraint with T of n is lesser than or equal to c into g of n. Then only we can say that your time efficiency function, that is T of n, belongs to big O of g of n. Okay, for all every given g of n. So now, so for if we draw the graph versus your T of n and g of n versus your input n. So before that drawing the graph, let me tell what are all the things are. So your T of n, that is nothing but the time efficiency function whatever you are going to get. Okay, that is the T of n function, and c into g of n. So that is nothing but the number of times your basic operation executed. Whatever the polynomial equation you have obtained that are going to be represented using some other function. So that is c into g of n for all the constant value c. Okay, and which for all the values of n which is greater than or equal to n naught. So n naught is the absolute value till that value, so this may vary. Okay, so sometimes your T of n may greater than this c into g of n, or your c of n may be greater than your T of n. Okay, but after this n naught, okay, this criteria should holds good. The constraint should be holds good, then only you can say that your T of n belongs to c into g of n, that is big O of g of n. So if I want to tell that, so that is your T of n belongs to big O of g of n, this must holds good the property of T of n should be lesser than or equal to c into g of n. So if I draw the graph for the given functions, that is T of n and g of n, so now versus your n inputs. So that is, if you consider this one as your n inputs, and if you are, so here you will be having two curves. One is for the function T of n whatever you have obtained. Okay, so that is your T of n function, and then so we need to represent in some order of growth, right? So for that we need to convert that equation into c into g of n such that it should be greater than what? T of n. So versus this one versus c into g of n. If you draw this curve, how exactly it look like is, so this represents, so these are all what? N values. So after some values, absolute value we can say, after this value the curve should be greater than, your T of n should be lesser than what? C into g of n. So that represent the upper bound of the algorithm. That is nothing but your T of n at any given point of time or for any given inputs, it is not going beyond your c into g of n. Okay, so that will be the worst case. So that is, so here if I draw versus n versus your T of n, so let me take this graph as like this. Okay, so this is your f of n curve, sorry, T of n curve. T of n curve. Okay, and now if I want to draw the c into g of n, So this C into G of n should be greater than this T of n. Why? Because according to this criteria, so we can say T of n belongs to your G of n if big O of G of n if and only if your G of n should be greater than what? Your T of n at any point of input. So that is after n naught. So for all the given inputs, your C into G of n should be greater than what? Your T of n. Therefore, the algorithm efficiency will be under this C into G of n times only. It won't go beyond that. Okay. So therefore, this represents the upper bound of the algorithm. So that's why it is called as an, so here whatever it might be, but after this point, that is absolute point. So here from this point, this curve should be greater than this T of n. So that is C into G of n. See, according to this criteria, the constraint itself, we can say that this represent what? The upper bound of the algorithm. What does this upper bound of the algorithm means is, so for any given set of inputs, okay, so your C into G of n will be the greater one. So for any set of input, your T of n will lies under this C into G of n only. It won't go beyond the C into G of n. So what is that C into G of n? That is nothing but the converted equation or the transformed equation of the equation whatever you have obtained while analyzing the algorithm. That is nothing but your time efficiency function. But here, while representing the time efficiency of the function, we need to represent in what? The order of growth of the algorithm. So in order to represent that, we need to convert that equation into C into G of n format. But here, if I want to represent my algorithm efficiency in terms of big O, then it should holds good the property of T of n should be lesser than or equal to C into G of n. Okay, this is the criteria we need to look. Okay, so if I draw the graph versus your n versus your two different functions, that is T of n and C into G of n function, the curve whatever we have, that is the T of n curve should be lower than your C into G of n. So for n number of values. So after this n naught only. Okay, until unless you obtain the constant value here, up to that, so whatever the curve status it might be, we won't bother. After this normal absolute value, your T of n will be lies under this C into G of n, which represent the upper bound of the algorithm. So whatever the equation you have obtained, it will comes under that equation only. Okay, so that order of growth representation is called as an, that belongs to what? The big O of that order of growth, which is going to be represented you for the worst case efficiency of the algorithm. Since it is representing what? The upper bound of the algorithm. Definitely it won't go up to that extent. Okay, it will come under that extent only. So because of that reason, your T of n belongs to big O if and only if your T of n is less than or equal to C into G of n. So then we can say that what? Your T of n belongs to big O of G of n. Okay. So this is about the big O. We will take the example once I complete the all the notations. Okay, definition of the notations. So if I come up with the next definition for this big omega. So as we discussed, so if T of n for every input, whatever the input it is, okay, as your input grows exponentially, so T of n always lies under your C into G of n. Then that algorithm efficiency belongs to what? A big O of that algorithm efficiency G of n. Okay, so this is about big O. So the next one whatever we have is big omega. So big omega, so for that big omega, so what we can do is just I am going to change this no other changes. Okay. Of n belongs to big omega of g of n if and only if your t of n is greater than or equal to c into g of n. Okay, the order of growth of the t of n is always greater than or equal to c into g of n. Obviously, if you are constructing the graph t n versus t of n and your c into g of n, definitely your t of n will be maximum and your g into c of n comes under this t of n. So, it is going to be represented the lower bound of the algorithm. So, for any given inputs, it will be the beyond this c into g of n. Okay, so that is the maximum extent we can reach. So that is the upper bound, so the lower bound of the algorithm. So your time efficiency function will come under only this t of n. So that is the big omega notation is. Okay, big omega notation is the one. So if I say t of n be the function of time efficiency function of any algorithm, the function t of n is said to be big omega of g of n if and only if your t of n is greater than or equal to c into g of n for any constant c and for all n greater than n naught, where n naught is the absolute value. So, from where which we are going to consider those points. Okay. So, for any point of time your t of n will be the upper bound and your c into g of n will be the lower bound. So, that is your algorithm efficiency is going to be represented for the lower bound. So, to represent the lower bound of the algorithm efficiency, we are going to make use of what? Big omega notation for at any point of time or for any given inputs. So, your t of n will be the maximum one. So, your c into g of n will come under this only. Okay. So, that is your big omega notation. Only the difference is, so for big O it is lesser than or equal to, and for big omega it is t of n should be what? Greater than or equal to c into g of n for all n greater than n naught. And so if I draw the curve, so definitely your t of n will be the upper bound and c into g of n will be the lower bound. Therefore, in order to represent the algorithm efficiency in terms of of the lower bound of the efficiency, so by that time we are making using of what? Big omega notation. That's why I have told that if I am going to represent the best case efficiency of the algorithm, then we are going to make use of this big asymptotic notation called as an big omega. Okay, so this is about big omega. Then what about this big theta then? So worst case is done, average best case is done, now left out with the average case. That means that your time efficiency function is going to be lies between two different functions. So then algorithm efficiency can be represented for the worst case efficiency, that is the big theta notation. So let t of n be the time efficiency function of an algorithm. The function t of n is said to be or belongs to big theta of g of n. So that is denoted by t of n belongs to big theta of g of n if and only if so I will write it here. The constraint is C1 into g of n lesser than or equal to t of n lesser than or equal to C2 into g of n for all n greater than or equal to n naught. This is the constraint. Okay. So here your algorithm's efficiency, that is T of n, lies between the upper bound and the lower bound of your algorithm. See, if you consider this is nothing but what? This part is nothing but your upper bound. Right. So if you consider this one, this part, this is nothing but T of n is greater than this one. So big omega notation whatever we have used. So this is for what? Lower bound. So in order to represent the algorithm efficiency of the lower bound term, then we will go for what? Big omega, right? So if you consider this, so this will be the lower bound and this is the upper bound, that is nothing but your big omega. And here, according to this constraint, whatever we have written, that is T of n lies between what? C1 into g of n and C2 into g of n. If you consider this equation, definitely this is the upper bound and the lower bound. So big theta notation is going to be represented if and only if your T of n, that is algorithm efficiency, lies between any two, that is the upper bound and the lower bound, then we are going to represent using big theta notation. Okay. So your T of n is going to be lies between the upper bound and the lower bound. So that means that, so here if I draw the graph, so definitely, so here one more, this is C1 into g of n, another one is C2 into g of n. So in order to represent the upper bound, so we are going to make use of C2 into g of n. So that is, this is the C2 into g of n. In order to represent the upper bound of, lower bound of the algorithm, so one more curve we have, that is called as an C1 into g of n. Okay. So this is your lower bound, this is your upper bound. So your T of n lies between your C1 into g of n and C2 into g of n. So your algorithm efficiency is going to be lies between what? This equation to this equation. Usually whenever we are going to represent our algorithm efficiency for the average case, then we are going to make use of the asymptotic notation called as an big theta. That means that for any given inputs, the algorithm behavior is going to be changed based on what? The upper bound and the lower bound. So that is C1 into g of n and C2 into g of n. So this T of n is going to be lies between these two function only. Okay. So then we can represent your T of n using big theta notation. So that means that, so whatever it is, big omega or big theta or it might be big O, so we need to hold good that property in order to represent of our order of growth of the algorithm. Okay. So let us take simple example and solve it in all the representation, or else we are going to represent using big O, big omega and big theta. Okay. We will consider simple example, simple equation, and then we will represent in big O, big omega, big theta. And remember, so whenever we are representing the equations, okay, so either in the big O, big omega, big theta, you need to remember this equation. What is that equation? Either this part, so that is T of n should be less than or equal to C2 into g of n, or else C into g of n. So if you are going to represent in what notation? If you are going to represent in big O notation. So if I want to represent in big theta notation, then this part. So that is your T of n should be greater than or equal to what? C into g of n. Then it can be represented in the time efficiency function can be represented using big omega notation. If your T of n is lies between two different functions, then it is your big theta notations we can make use of. Okay. And then using big theta notations we can represent our algorithm efficiency. What all the given is? Thus the given is T of n is equal to 100n plus 5. So in what notation we need to represent? We need to represent in big O notation. Therefore according to the big O notation, so T of n is said to be belongs to big O of g of n if and only if it belongs to what? Your T of n should be lesser than or equal to C into G of n for all n greater than or equal to n naught. It might be equal to G of n equal to f of n or T of n, okay, but it should not go lower than that C into G of n at any point of time, okay. So now we need to, so we know that what is T of n? 100 n plus 5, and we need to obtain the equation, that is the equation whatever we have, that is 100 n plus 5 in terms of C into G of n format, okay. So here we have a higher order degree, that is 100 n, that is the power of 1. So higher order degree of this equation is what? 1. So for this is n to the power of 0. So highest order degree of this equation is what? 1. So we need to consider this number. So that is n we need to consider, okay, and the lower order terms can be neglected or we can represent in some other way, okay. So now we need to convert this T of an equation, that is 100 n plus 5 by in this format. So that is C into G of n format, okay. So for that what we can do is, let us take equation, so let me call this equation 1. So here what is that equation is? T of n is equal to 100 n plus 5, okay. Now we need to convert into its equivalent form to C into G of n, okay. So you should get a multiplicative constant for the G of n. So what is this G of n is? So for any point of time we need to, in this equation, that is 100 n plus 5, the whatever the highest order degree of that equation we have, right. So that we need to consider as in G of n, okay. In the polynomial equation 100 n plus 5, n is the highest order degree, that is 1 is the highest order degree. So that term we need to consider. If I consider only 100 n, what happens? So 100 n plus 5 less than or equal to 100 n. If I consider only 100 n, by that time what happens? If I give any values, so for example n starts with what? 0, 1, 2, 3, 4, etc. right? So now if I give the value for n is equal to 0, now what happens? 0 plus 5 is 5, 5 less than 100 into 0 is 0, 100 less than or equal to 0. Is it true? False. If it is false, so definitely, so whatever the value I have taken, that is wrong for any input. So if I increase n is equal to 1, by that time also this equation will be false. Say for example 100 into 1 is 100, 100 plus 5 is 105 is less than or equal to 100, that's it, okay. So then also it is what? False. So if I give n is equal to 2, by that time also, so 100, you have a 100 n, okay, along with that you are adding 5, so extra 5 you are adding, definitely the left hand part will be greater than what? The right hand part. So now 100 n is not our C into G of n, therefore what is that C into G of n is? Okay, so that we need to calculate. So how we can consider is, just replace your lower order term equation into the higher order term, okay. Just replace the lower order term into higher order term of that particular equation. What is the higher order term? Here it is n. So lower order term is what? 5 into 1. So just convert that 5 into 5n, that's it, okay. So convert the lower order term into higher order term. So by replacing lower order term to its higher order term, what you will get? Definitely it will be 100 n plus 5n or just n. Okay, it is up to you. If you want, so to replace the entire lower order term with n, it is up to you. If you want, you can replace like that also, or else directly we can replace this value to n directly. Okay, I will tell you, we will discuss if I am replacing with 5n, what happens. If I am replacing with only n, what happens. Okay, let me take the example. So now let me complete this. 100n plus n is what? 101n. Okay, so this is your, so 100n plus 5, this is your t of n, and this is your what? C into g of n. Okay, C into g of n. See, so algorithm efficiency has to be represented using order of growth. Either it might be linear, it might be quadratic, whatever it is. So that is n. So highest order degree of this equation is n. Only in n only we need to represent. So therefore, what is that C is we need to identify. Okay, so n is nothing but your g of n or your t of n. So definitely your C varies. So what is that C is we need to calculate here, and also what is that n naught is we need to calculate. So let us see, in order to calculate the n naught, just give the value for n values. Okay, let's start with n is equal to 0. So let me apply here itself. Okay, so whatever the value I have taken, 101 into n for all n greater than or equal to n naught. N naught is, so here we need to find out this n naught. So in order to find out the n naught, give the values for n naught here. Okay, sorry, for the n values. So n starts with 0. Let us give the value n is equal to 0. At n is equal to 0, what happens to n t of n? What happens to c into g of n? Let us see. Okay, so 100 n. So 100 into 0 plus 5 less than or equal to 101 into 0. What happens? So 5 less than 0, false, right? So now increment the n value by 1, n is equal to 1. So now what happens? 101, 100 into 1 is 100, 100 plus 5 is 105, less than or equal to 101 into 1, that is nothing but 101 itself. But still 105 is less than or equal to 101 is false. If it is false, just give the increment the value of n. N is equal to 2. So if I give the value for n is equal to 2, what happens is, so 100 into 2, 200, 200 plus 5 is 205 is less than or equal to 100, 101 into 2 is 202. So this is also false, since 205 is less than or equal to 202 is false. So less than, this is greater than this, that's why. So increment the n value by 1, that is 3, that is 305 is less than or equal to 303. Again it is false. So n is equal to 4, 405 less than or equal to 404. This is also false. So when n is equal to 5, what happens? 505 less than or equal to 505. Yes, now the condition holds good. Since 505, that is t of n, is equal to c into g of n, that is 505 itself, right? So if you give the value for n 101 into n, then you will obtain what? 505. So now let me check with the next values also, that is when n is equal to 6, what is the value? So 605 less than or equal to, so 6 into 101, that is 606. Yes, so this part is greater than this. C into g of n is greater than t of n. This is also true. So if you keep on giving the n values here, so definitely the right hand side will be greater than the left hand side. So this point is called as your absolute point. So that means that after this value, even if you give n is equal to 100, by that time also this condition is going to be holds good. Okay, so that equation, okay, whatever the constraint we have used, according to that we need to write it. So just by comparing this equation, let me call this equation as 2 and this equation as 1. Okay, by comparing the equation 2 with the equation 1, Okay. So let us take the example here. Just compare by comparing, what we can write is by equation 1 and equation 2, what we can say, your C is equal to what? 101. For all given values of C is equal to 1 and your G of n is equal to what? Your G of n is nothing but your n. Okay. G of n is equal to n for all n greater than or equal to n naught. What is your n naught? That is the absolute value. After that value, your condition whatever you have, the constraint whatever we have, that will be holds good. That property will be holds good. That point is called as an absolute point. This n is equal to 5 is your n naught. Okay. So this is n naught. So in order to remove your confusion, let me draw the graph itself. Okay. So now C is equal to what? 101. G is equal to what? N, and for all n greater than or equal to n naught. What is your T of n? 100n plus 5. So for the given equation 100 n plus 5, so what we can say, your T of n belongs to big O of G of n. What is G of n? G of n is nothing but the value n. So like this we can represent. So or else we can say 100n plus 5 belongs to big O of n for all set of n inputs. So this algorithm efficiency lies under this T of n only. Okay. So that is your big O notation. So let me talk about this absolute value here. So for that, if I am drawing the graph here, okay, so I have given the value started with 0, 1, 2, 3, 4, 5, 6. So I will take the input 0, 1, 2, 3, 4, 5, 6, 7, etc. And if you observe here, so your C into G of n or T of n is 100, 200, 300, 400 like that. Here also it is 100, 200, 300 itself. Okay. So for that I am taking the value for C into G of n, and for your T of n what I am going to take is 100, 200 to mark the points, 300, 400, 500, 600, 700. Okay, just to mark the point I am using this. Okay, so I am going to use pink color for representing the T of n curve, and the white color I am going to represent it for C into G of n. Okay, so first let me take your T into G of n values. Okay, so when n is equal to 0, what is your value? 5, right? So when n is equal to 0, your C of n is what? 5. Okay, and your G of n is 0, 0 only. So at this point only. Okay, so now when n is equal to 1, when n is equal to 1, your value is what? 105. And what about this? 101. So first let me draw fully the T of n. Okay, so let me mark the C of n only. When n is equal to 1, your curve is 105, that is above this point. Okay. Next, after that, when n is equal to 2, 205. Here it comes. And when n is equal to 3, 305. When n is equal to 4, 405. When n is equal to 5, 505. When n is equal to 6, 605. Okay. When n is equal to 7, 705. Somewhere here. Okay. This is what? This is your T of n curve. Okay. So let me draw the C of n curve now. Okay. When n is equal to 1, 0, it is 0. When n is equal to 1, it is 101 under this. Okay. And when n is equal to 2, 202, 303, 404. So 505, exactly same point. When n is equal to 6, 606. That is above this 605, right? So when n is equal to 7, so if you give the value for n is equal to 7, what happens? So 705, and lesser than 707, right? So if it is a 707, now what happens? So the curve might be comes here. Okay. So now if I draw the graph or if I join these points, now what happens? See, up to this point, absolute point, your curve T of n is above this C into G of n. Now what happening? So once it reached the 5, okay, after this 5, what is happening? So curve will grow on top of this C in T of n. So that is your C into G of n will be the upper one, lower to this T of n. Therefore, in order to represent the upper bound of your algorithm, we are going to make use of what? Your big O notation. So algorithm efficiency comes under this only. So okay. So worst case it is go up to what? C into G of n only. It won't go beyond that. Okay. So that's why in order to represent the worst case efficiency of the algorithm, we are going to use what? Big O notation. This is how we can represent the, for the given equation, we can represent in big O notation. So in the next class, we will learn how to represent in big omega and big theta with the same example. Okay. Thank you.